Day. Welcome back again to the next lecture on Geotechnics 254, and we are looking at soil conditions and flow through soil at the moment. This particular picture I took just outside of Gordons Bay on Clarence Drive on the way to Rooihouse. This is clearly not a homogeneous soil, and it's also not isotropic, and it has some form of layering in it. So we're going to look at this kind of condition for today's lecture. It's about anisotropic soil conditions, and it's in the handbook chapter 2.5. Up to now, we've looked at isotropic soils. In other words, the total soil package have only one K value, one coefficient of permeability. The soil, however, is in real life, soil, however, is mostly anisotropic with different properties in different directions. Layered soil is a good example of that. So here, the permeability Kx in the x direction is typically higher than in the in the z direction. This is especially true for layered materials. So we're going to look at the flow nets for anisotropic soils. Because the two Kx differs from Kz, with Kx typically being larger, the soil needs to be transformed to have imaginary isotropic properties, with the transformation factor is based on the permeability. And normally we transform the x direction and not the z direction. Because now if we have imaginary isotropic properties, then the equations are valid again. So Kx is not equal to Kz for anisotropic soil. In other words, the Laplace equation no longer applies. To get around this, we need to transform the geometry of the structure so that we can do a graphical flow net exercise. So if Kz is 2 times 10 to the minus 8, sorry, that shouldn't be 2 divided by 10, it's 2 times 10 to the minus 8, and Kx is 8 times 10 to the minus 8 meters per second. We have a factor xt, which is the square root of Kz over Kx times x. Substitute the values, and we now get a value of 0.5x. So the transformation factor xt equals 0.5x. X is the z direction. Modify the geometry by this factor. So this will change a rectangular block in a flow net to a rectangle of length 0.5. So the K value for this transform, which we now assume to be isotropic soil, is calculated in the following manner, and that gives us a new value for K, 4 times 10 to the minus 8 meters per second. And essentially what it means is we have now squashed essentially the structure in the x direction. The dam wall is now shorter so that x and z K values are equal. So the flow net blocks for an anisotropic soil are rectangular due to dn being larger than ds. In other words, it flows faster in the x direction. This is what the flow net will look like for the original structure, but once converted, we squash the structure. dn and ds now becomes equal again, and the normal rules apply, and you can do your flow net and you can do all the equations and exercises as if it's an isotropic soil. If we have flow parallel to the layers, then we have a flow in first layer, which have a K1 and a height 1, and Q2 is the flow in the second layer, and it combines for the total flow rate, Q. So if Q1 is this and Q2 is this, then the total flow rate can be derived, and we get to the point where we say the total flow is Q1 plus Q2, and therefore we do all of this mathematics, and in the end we say the k in the x direction is equals to the sum of k times h over the sum of all the h's. Because there's different layers, so if we go back to this drawing, there's the h for this layer, and h for this layer, and h for another layer, etc. And we end up with, for kx, we end up with this formula. If we have perpendicular flow, remember we still have h1, h2, h3, k1 in this layer, and another k, excuse me, no, that way, another k in the other layer, etc. And this is the change in x direction over distance. And again, we now say Q equals Q1 equals Q2. The total flow rate becomes this formula, and right up to the end we say if Q is this value, we have a Kz of all the sums of the h over the sum of h divided by k. In this particular case, we have two different soils meeting at a certain point and at a certain angle. So we have a delta N1 and delta S1 in this particular soil, and a K1. And in this soil, we now have a K2, where we have faster flow in this direction, and delta N is this value. And this is the change in flow rate over distance. So delta Q, the change is K1 over delta H, delta H over delta S1 times delta N1, and it's equal in K2. If we add all this together, we say that if delta S over delta N equals 1 in layer 1, it comes down to that for layer 2, delta S over delta N is equal to K2 divided by K1. This is the same drawing, but just with all the different angles and values in order for us to do some mathematics. So delta S1 is AC times sin alpha 1, delta N1 is AB cos alpha A1 S2 and N2. So therefore delta S1 delta S1 over delta N1 equals AC over AB tan alpha 1, and delta S2 over delta N2 equals AC over AB tan alpha 2. And in the end we say K1 over K2 is equals tan alpha 1 tan alpha 2. Go back to the drawing in order to make sense of the mathematics. This is simple mathematics that you all did at school, and then you can get the relevant values and solve for a particular value.